I'm going to use another method to show that angles B and F are congruent. As I mentioned in the former video, students who are good at proofs will be able to notice that there are multiple methods that they could solve a problem, and they'll be able to choose the one that is easier. This method that I'm about to use does not follow the pattern that I've been mentioning in all the other videos. In fact, it doesn't even prove triangles are congruent at all. But I think it is a faster method. It requires less steps than the other proof. Once again, I will encourage you to not be writing as you are watching this video, but rather to see the video and then see if you can understand it enough to replicate it on your own without a video in front of you. I'm going to, the goal having been proving B and F the same, start with the givens. The first given is that BC is the same as EF. The second given is that side DC is the same as side DE. I went through a pretty long explanation about the addition postulate and the segment addition postulate in the former video. So if you would like to see a more detailed explanation, you can watch it in that video at the beginning. But all I'm about to do is add the two pieces here, the red and the blue, and say that if I add the red and the blue, they should be the same length as this red and the blue, because the blues are the same and the reds are the same. So if these were 5 and these were 10, the whole thing would be 15. I'm just doing that without numbers. I'm saying that if I add BC, this blue, plus CD, it will be the same size as FE plus ED. So on the left, I have the first blue one, that BC, plus the red one, CD, will be the same size as the blue one, FE, plus ED, because I already know that the blues are the same as each other and the reds are the same as each other. This is the addition postulate. I'm going to now combine and say that, well, if I add BC plus CD, the blue plus the red, that just gives me the black. So BD is the same as FD. This is the segment addition postulate. From here, I'm going to entirely choose to skip this given because I've recognized I do not need it. What I've just shown in step 4 is that this long side BD is the same as this long side FD. And if I were paying attention, I would recognize that they are both sides in this large green triangle. And if I have two sides that are the same in a triangle, that is called an isosceles triangle. So at this point, because those two sides are the same, I can say that the big green triangle BDF is isosceles by definition. So I knew that two sides were the same because of the segment addition postulate. So therefore, if two sides are the same in a triangle, the triangle is an isosceles triangle. And the cool thing about isosceles triangles is that not only do they have two sets of sides that are the same, but they also have two sets of angles that are the same. And in this case, that is going to be angle B and angle F. So I found out that the two sides were the same using the segment addition. I called the triangle isosceles because it had two sides that were the same. That's the definition of isosceles. And if you have an isosceles triangle, you also have two congruent angles. This is the definition of isosceles. So you'll notice for this proof, I did not at all use this method. I never proved any triangles were congruent. I never showed the pieces were the same through CP/CTC. I was actually able to use a different method of showing the large triangle was isosceles, therefore its angles were the same. This was a faster method. The other one would work, but a good student will be able to recognize multiple methods and use the easier method to their benefit.